And we'll welcome back to the second half. And I'm very happy to say the second session is chaired by Jeff Raker from the Department of Chemistry in USF. Jeff, similar to Nicole, has very broad and intensive research interests across lots of different topics, but he does have the accolade for me in that he is the first person I ever heard talking about this strange world called machine learning. I mean, it's a long time ago, 7 or 8 years ago, and some really nice work in predicting, optimizing, evaluating things that we are talking about now. So I'm very happy to say I'm passing over to the another expert in this topic, and I will happily linger in the background. So Jeff, I'll pass over to you. Thank you very much.
Thank you, Michael. Thank you for the invite, and all of you that are here attending. This is exciting when you get this many people still at online events. I do want to comment on that talk that Michael heard, which is that I oftentimes get to speak and really on research that really the people behind the scenes are my graduate students and postdocs and collaborators that I get to work with. So actually that talk that Michael heard was work that Amber Dude, who you just heard from, with that. I bring that all up to kind of set the stage for this afternoon that we really have this afternoon. It's afternoon for some of you, it's still morning here in the States. For our two talks. When Michael approached Nicole and I back in January about this, we immediately were like, hey, there are experts and you should really talk to the experts. And we listed a whole bunch of those folks. And our next two talks are going to come from folks that are early on in their career, that are working with faculty members to not only become chem ed researchers and chemical educators in terms of their doctoral work, but their doctoral work is all part of this sphere. So our first talk is from Paul Martin, who works at Justus Liebig University in Gießen, and you may have seen our other chair behind. I value that everybody gets their own screen. Those are my rules in my group, that if we have two talks, you have to be on your own screen. But I'm going to turn the floor over to Paul, who's going to tell us about some exciting work that he's done in the field of reasoning, argumentation, using multiple languages, really kind of applying a lot of the things we've heard about today. Paul, the floor is yours.
Yeah. Thank you very much for your kind introduction. From my perspective, it's a good afternoon to every one of you from Gießen, and I'm really thrilled to be part of today's meeting on AI in chemistry education research, and I hope that you can now see my screen. Yeah, you already introduced me, Jeff. Thank you. My name is Paul Martin. I'm a PhD student at the Justus Liebig University in Gießen, and I'm so excited that you all are here to implement machine learning techniques, AI techniques to shape the future of chemistry education. And I hope that I can continue to provide some novel, useful insights on how to apply AI to catalyze innovations in our domain. In today's talk, I'm going to focus on using so-called multilingual machine learning models to allow multiple languages in our chemistry classes. And I'm going to focus on 4 different topics today. At first, I'm going to give a short introduction on how linguistic diversity impacts science learning. After that, I'm going to introduce the instructional setting that we used in our simulation study to test the effectiveness of different mono and multilingual approaches to allow different languages in our classes. The third part of today's presentation is a bit methodological in nature, because here I'm going to validate all those different approaches. And finally, I'm going to give a short outline on what you can do to allow multiple languages in your chemistry class. But let us start with talking about multilingual learners and how linguistic diversity is impacting science learning. Chemistry education practice has shown over the last couple of decades that linguistic diversity is increasing in our classes. So the language of chemistry instruction does not necessarily correspond to a student's first language. And consequently, language learners often face challenges in language acquisition, in science learning, but also and most importantly at the intersection of both. And therefore, additional barriers arise for all those students to actively participate, to actively engage in our chemistry classes. Indeed, there are language barriers which hinder effective communication, impede the exchange of ideas, and potentially exclude valuable contributions from all those English learners. Additionally, language learners, not only in English, have often challenges in understanding, communicating, and applying domain-specific chemical concepts, for example, in chemistry. In a recent study, Jackie Deng and his research team could show that language learners constructed the fewest amounts of causal arguments at all. So language learners often face challenges in constructing well-justified evidence-based arguments. These students also have extrinsic and intrinsic challenges in engaging in lectures and comprehending laboratory procedures. Despite strong content knowledge, they may lack the fluency to fully express their ideas in the language of instruction. Besides, cultural or linguistic references in science assessments may not be readily accessible to all those students. Especially, language learners often face challenges in grasping the intended meaning of terms. For example, when the everyday and scientific meanings of these terms diverge. And these language learners also have feelings of anxiety about their language usage. So all this body of literature indicates that students' performance in science assessments is linked to their language proficiency, at least to some extent, irrespective of their real capacity to apply and comprehend scientific principles. And therefore, as a community of chemistry educators and chemistry education researchers, we may have a shared mission. We may have the mission to allow all those students to show their full scientific understanding, at least to some extent, irrespective of their language understanding capabilities. Of course, there are different approaches. It is important that we provide all those students with opportunities for a continuous language development. Continuous language development is important so that students can gradually improve their skills. This can help in everyday life and in chemistry learning, but we are going to talk on AI today, and I'm going to present another approach. We could also use AI techniques, for example, machine learning and natural language processing, to allow all those students to choose the language in which they want to complete our exercises, for example, in formative assessments. I'm going to talk a bit about that claim. In a study already mentioned by Jackie Deng and his colleagues, they could show that most language learners prefer the language of chemistry instruction to communicate on chemistry assessments. However, not all students shared this preference. Some language learners also claimed that they can advance their reasoning about chemical phenomena by using their first language. And to increase equity, linguistic diversity for the latter students, we could apply different approaches. An easy to implement opportunity here on the left is to use one of several translation tools like Google Translate, DeepL Translate, or ChatGPT to translate back and forth between different languages. Due to so-called attention mechanisms, all those translation tools have significantly improved within a relatively short period of time. So we could use a single tool to translate students' reasoning in any language back into the instructor's language. But we could also develop multilingual AI models that can automatically evaluate students' reasoning in any language or across different languages.
Paul, I'm going to quick interrupt you. Your slides disappeared.
They disappeared. Oh, then.
They're okay for me. I still see them.
But... Yeah, I still see them too.
Okay, thank you.
Okay,
then
we're good. We're good.
Okay, then I can continue. Thank you for your hint. Yeah, we could also try to establish these multilingual AI systems that can automatically evaluate students' reasoning across different languages. And we already talked on that. Developing these AI models is a bit resource intense, but once developed, the evaluation process is fully automated. A multilinguistic approach to developing these AI models may also acknowledge students' linguistic diversity, and so we may mitigate some fundamental concerns that AI algorithms take a majority-driven language as a benchmark against which all other text data is evaluated. In today's talks, Amber and Markus already introduced some AI and machine learning basics. Therefore, I'm only give a short contextualized introduction for my research purpose here. Machine learning deals with developing algorithms that learn automatically from data to make predictions in new situations without explicit programming. Machine learning can be roughly classified into unsupervised techniques and into supervised techniques. Unsupervised techniques extract patterns in data on their own. Clustering techniques are often unsupervised machine learning techniques, so they group data points into distinct categories. We used supervised machine learning for our research purposes. Before using supervised machine learning, humans have to label data. The data already contains the known output known as ground truth, and the algorithm then discerns the underlying patterns, tries to model relationships, and reproduces human labels to a certain extent of accuracy. Over the past about 15 years, these supervised machine learning techniques are increasingly applied in science education research, and they led to significant advancements in automatically evaluating students' reasoning. We also talked about natural language processing and large language models. To allow computers to analyze human language, text data must undergo pre-processing using suitable natural language processing techniques. And for example, large language models, as most prominently recognized in ChatGPT, can be used for natural language processing purposes. These large language models are trained on large extensive text corpora to extract intricate patterns from language data and to produce contextually relevant responses. Typically, large language models operate on huge deep neural networks consisting of multiple layers of interconnected so-called artificial neurons. These deep neural networks are inspired by the structure and function of the human brain, and through a series of mathematical calculations, these deep neural networks convert natural language human text data into so-called contextualized embedding vectors, which are high-dimensional numerical representations of words in a sentence. As Amber already mentioned, we used BERT for our research purposes here. BERT was developed in 2018 by Google. BERT is specifically trained to capture semantic relationships between words in a sentence, irrespective of their distance. There are hundreds to thousands of different BERT models today, and we can download such a pre-trained BERT model, and we can then fine-tune these BERT models for our domain-specific needs, for example, to classify students' reasoning in a science assessment. For example, if we want to classify students' English written responses, we can download English-specific large language models. There are also German-specific large language models, for instance. These so-called monolingual large language models are tailored for an in-depth analysis of a specific language and offer a nuanced understanding of that language. But there are also multilingual large language models which can evaluate student response, for example, across different languages. They show high generalizability in many languages, but often lack a specific understanding for a single language. And now I'm going to present the instruction setting that we used in our simulation study to validate these different approaches. We built upon an instruction setting that was designed by Leonie Lieber and Nicole. They prompted students in undergraduate organic chemistry to judge the plausibility of alternative reaction products for competing chemical reactions. Here, for example, for an intramolecular Williamson ether synthesis. And these 4 alternative reaction products were sequentially displayed to the students. The products that are highlighted in red are implausible reaction products, and the green ones are rather plausible here. And then students had to make a claim on a product's plausibility. They had to back this claim with open-ended evidence statements that often refer to chemical information or chemical concepts. And finally, they had to justify the linkage between claim and evidence by integrating electronic, steric, or energetic properties of the involved molecules. We then used 2 theoretical frameworks pertinent to chemistry application research to classify students' open-ended reasoning. On the one hand, the levels of granularity, and on the other hand, the modes of reasoning. The levels of granularity classify the depth at which phenomena are explained, and we used at the top of this figure 2 different levels of granularity, structural and energetic, to identify the topic students reasoned about. And then we also apply 2 other levels of granularity, which are phenomenological and electronic. Here in the middle of this figure, phenomenological stands for surface level accounts of these organic chemistry reactions, and electronic reasoning often included electronic properties like resonance, hyperconjugation, or inductive effects. And Sebin and Talanka's modes of reasoning comprise the second dimension of our scoring rubric. These modes of reasoning classify student sophistication in establishing connections between different chemical concepts and providing justifications for why transformations occur. And we applied 4 modes of reasoning with an increasing level of causality here, ranging from absent to linear causal. And then we tested all those different mono and multilingual approaches to analyzing students' reasoning across different languages. First, we had some research questions in mind here because instructors are not expected to be fluent in every language, so questions of reliability arise, and we addressed all those research questions by simulating the language transition between English and German, as both Nicole and I are fluent in these 2 languages. First, we wanted to identify the best performing translation tool in our domain in chemistry education. As hundreds to thousands of different large language models exist, we also needed to identify the best performing large language model. Then most importantly, we compared the reliability, the performance of different mono and multilingual approaches to analyzing students' reasoning. And finally, we also used so-called data augmentation strategies to expand our training data size and to improve the performance of our models. We used the 1,100 English written scientific arguments collected by Leonie Lieber and her research team that investigated students' argumentation skills in undergraduate organic chemistry. We scored all those arguments using our holistic 20-category rubric, and then we developed an English-specific machine learning model. This model has an accuracy of 0.8711 and a Cohen's kappa of 0.8610. The higher these values, the better a model. Accuracy only measures the percentage of agreement between human and machine scores, and Cohen's kappa also counts for agreement beyond chance. And then we used the 3 translation tools, Google Translate, DeepL Translate, and ChatGPT to translate students' English written arguments into the German language. And then we trained 3 separate machine learning models, one per translation tool based on the 1,100 translations, and assessed their performance. So human raters did not score the quality of all those translations. Rather, we used a machine learning model to evaluate the consistency with which these models can convert the translations, the German translations, into labels. And here you can see the performance of the different translation tools. You can see that only minor performance variations are evident across these 3 translation tools. Google Translate and DeepL Translate tended to perform a bit better because ChatGPT occasionally paraphrased or added some sentences, which led to modifications of phrases relevant to coding. And we also compared our results to some rather domain general studies, and they also indicated that the performance of translation tools is significantly dependent on the context of the text and of the language pair used to translate between text data. But most importantly for this research question, we showed that the performance of translation tools is acceptable. It is still crucial to compare the performance of different translation tools in a specific domain, but in chemistry education, Google Translate and DeepL Translate seem to be the most appropriate tools. We then used only the German translations of the English written arguments to train 6 different large language models, and then we analyzed their performance. So we had a machine learning models, 6 at all, 1 per translation tool, and we compared the performance of 3 monolingual and 3 multilingual machine learning models here. At the top, 3 monolingual German-specific machine learning models, and at the bottom of this figure here, 3 multilingual machine learning models. And we hypothesized that the German-specific models would significantly outperform the multilingual ones because the German-specific large language models are specifically trained to analyze the German language. But we were surprised by our findings. Although Gottbert Case here in the top right corner performed best, 2 multilingual large language models, the Roberta models, performed nearly as well as Gottbert. And this already shows the great potential of the multilingual large language models in analyzing students' reasoning in a single language here in the German language. And this motivated us to further investigate the performance of all those multilingual large language models. And we now switched from a monolingual context to a multilingual context. We now trained the 3 different large language models on both English written arguments and their German translations, and we assessed their performance across these 2 languages. The performance indicates that the English-specific model on the top left corner here outperformed all other models, but especially multilingual BERT performed nearly on par with our German-specific model. And this again shows the great potential of all those multilingual models to analyze students' reasoning across different languages. So based on these multilingual large language models, educators could develop machine learning models that allow students to choose the language in which they want to complete, for example, a formative assessment in chemistry. We already talked a bit about bias. We now saw that we could not upheld performance of our machine learning models across different linguistic contexts in detail. The performance of the German-specific model was 5% less than that of the English-specific one. And therefore, we finally looked for easily implementable ways to increase the accuracy of our German-specific model. Therefore, we combined the translations of the 3 translation tools to triple the amount of training data the German-specific model is trained on. But unfortunately, we found only slight increases in machine-human score agreements. And this indicates that the application of machine learning is, in our context, biased towards the language students use. But that were already the main findings, and I only want to give you a short overview of what you can now do to allow multiple languages in your chemistry class. We validated different mono and multilingual approaches to analyzing students' reasoning across two languages. When aiming to translate students' reasoning into another language, translation tools can be used, and Google Translate as well as DeepL Translate performed best here. But we could also develop machine learning models that can automatically assess students' reasoning across different languages. The multilingual large language models showed here great potential in analyzing students' reasoning across German and English. So we could develop machine learning models, including multilingual large language models for natural language processing. To generate corresponding multilingual training data sets, instructors could capture students' reasoning in a single language, could then use a suitable translation tool to translate that reasoning into any other language, and so create multilingual training data sets to train a machine learning model across different contexts. And in the future, this may ease effective communication across different languages in our chemistry classes and may allow students to choose the language in which they want to complete assessments. Finally, we see two things which can be done in future research. As mentioned earlier, the performance of the English-specific model was still much better than that of the German-specific one. Collecting additional student data can be a first step in improving model performance, but we could also investigate to what extent generative AI can be used to create so-called synthetic data and to boost model performance. And students may also switch between different languages in a single sentence. This practice is called translanguaging. Translanguaging often helps students who have to learn the language of instruction as a new language to make sense of chemical phenomena and to use their full linguistic repertoire. And machine learning could also be used to assess students' translanguaging. But at this stage, the only thing I want to do is to thank you for your attention, and I'm happy to receive any further questions. Thank you very much.
Excellent. Thank you, Paul. This is entirely insightful. I'm at an institution where a lot of students speak Spanish, and so there's that constant that we know students are translating between the two. So I think work like this is very helpful for that. Folks, we are taking questions from the chat, so feel free to drop those things in there. We have about 6 minutes here for those, so we'll do that. Paul, I'm going to start with a question that's in the chat, which has to do a little bit with the construction of language.